Hey guys. So in this one, we'll now get into torques a little bit more, and we'll look at something called static equilibrium. So static equilibrium means your net force is zero, so there's no acceleration. In these, this is typically going to be at rest, but it could be at constant velocity, and your net torque is also zero. Some other things that torque, the units are in newtons per meter. We said you could do R times F perpendicular, or we said torque equals F times the distance perpendicular, which is also equal to F times lever arm. So we'll be able to use those. We talked about things that affect the force for turning ability or its rotation. And so that's where that force is located. So if I was trying to rotate a wrench again, man, I can't draw. Right. So here's my wrench. If I put my hand right here and try and pull downward or pull out here, I'm going to get different torques because these both have different lever arms. So that's one. The magnitude pretty easily. If I pull hard enough here, I can get those to balance out. Then the direction which that force is exerted. So that would be if I took this force and I pull this way. Well, if I pull that way, there's zero torque as a refresher because there is no perpendicular force there. So that's what we have to watch out for. When we're doing this, as we do these, again, F nets and torque nets, now you're going to see signs are really, really important. So make sure you're focusing on these. Typically, we do positive is counterclockwise, negative is clockwise. It really doesn't matter, again, as long as you pick a direction and go with it. But we'll show you those. So, problem solving with these, it's back to the same. Be a kitten. Remember, just relax. Okay? Don't freak out. Just do the best you can and say, hey, I can do each of these little steps, especially if our free response on the AP test, they're just going to look for partial credit. So again, we're only for response, so we can see how we can do that. Draw a picture, that's always going to help. Have your free body diagram. Now when you do this, put the forces at their origin. So wherever those are, it matters now for rotation. We talked earlier, if I have a box, hey, if I push up here or I push here, those are totally different things. If I said this is A and this is B, A will cause it to rotate about its center if that's what our point is, but B, it will just slide and have no rotation, so that matters. Again, pick an axis and pick a coordinate and axis of rotation, and then you have your two equations. Again, we're eventually going to get to systems of equations, so you could eventually have three. Today, we'll only have two tops, but I don't think we'll even have to do systems yet. Right, but we'll look at some. So let's pick this problem. Now it gave us all the numbers, but let's try to solve it for one of these. Let's try to solve for F3. So when we do this, we want to see if we can get F3 equals 2 newtons. So let's test it out. So let's first draw in our forces. So I know I have F3 is pulling downward. Gravity is acting at the center of mass. F2 is going upward, and F1 is going downward. So let's do our F net. This is at equilibrium, so equals 0. Remember, arrows up minus arrows down is typically the way to do that. So I would say F2 minus F1 minus Fg minus F3 equals 0. Excuse me, let's plug in and see what we get. This is 9 newtons minus 6 newtons minus 1 newtons, and we're saying we're solving for F3 to see what we get. And so F3 equals 0. So 9 minus 7, so I have 2 newtons equals F3. Hey, that's what we had right there. So that worked. So I didn't even need torques. But let's see if it still is actually at equilibrium because the torques are canceling out. So here we have to say then the torque net equals 0. So we have to pick an axis of rotation when we're doing this. So let's say right here is where it rotates about. So we'll pick that as our axis of rotation, and you can see the numbers match up with that. Truth be told, you can pick anywhere, but let's go with that. So if we notice these, if I look at this one, if I did the lever arm, I could extend the force out, and it's going through the axis of rotation, so that one has no lever arm, so there's no rotation involving F2, so I won't put F2 anywhere in here. But if I look at F1, that definitely does cause a torque. And if I held my finger here, this would cause it to rotate that way. So that's counterclockwise. So let's say that's a positive torque. So I could say the torque due to 1. Let's see. Let's look at force of gravity. Does force of gravity cause a torque? Yes, I have a lever arm and a force. And so that would cause it to rotate the other way. So that would be then minus torque due to gravity. And then this one also has a lever arm. So then that's, and it's going to make it go the opposite direction. So that is torque due to 3 equals 0. Again, you don't put 2 in there because it does not create a torque because the force is at the axis of rotation. So now let's plug in what we know. So here I could say, well, this is force of 1 times the lever arm of 1 minus force of gravity times the lever arm of gravity minus force of 3 times the lever arm of 3 equals 0. And then let's plug in what we have. Force of 1, 6 newtons. And the distance I can see right here, that is 0.2 meters. Minus the force of gravity, it told us that is 1 newton. Times its lever arm, that is also 0.2 meters. Minus force of 3, that's what we're looking for to try and prove. And then the lever arm of that one, that is this distance here, so that is 0.5 meters equals 0. So, checking my numbers, let's see, this is going to be 1.2 newtons times meters, that's our unit for torque, minus 0.2 newtons times meters equals, I just added this to the other side. So I get 1 newtons times meters equals F3 times 0.5. So then F3, doing my algebra, is going to get me 2 newtons. And hey, what do you know? That's what I have. So here, we can see that it works when you're given everything. Again, either one can work. Always, I like to start with forces first, because if forces works, it's less complicated, and just solve it with forces. If you don't need to do torques, don't. Sometimes you'll see later on you'll have to do torques, so that's what you'll need, both of them. All right, let's try this one. I just want to show you that this still works from another perspective. So let's call F1 my axis of rotation. I know it's not rotating there, but let's just see if that was it. So forces would be identical, so we don't need to look at that. But let's say our torque nets equals 0. So again, putting my forces in, there's F1, F2, Fg, and F3. So I want to see how this would work from that being my axis of rotation. So from here to there, there is a lever arm and a force. And if I held this and pulled upward, that would make it rotate that way. Again, it's not actually doing this, but I can still solve any axis of rotation location and it will still work out. And you'll see why that's going to be useful in a little bit. So here I could say, then let's make that direction, that'd be what, counterclockwise, that's positive. So that'd be the torque due to 2. If I held here, again, that has a lever arm, that would rotate that direction, so that's the opposite, so that's a minus torque due to gravity. And then F3 would also be the same, torque due to 3 equals 0. Then I can go back, and that is force of 2 times lever arm of 2, plus force of gravity times lever arm of gravity. Again, you don't have to do lever arm, you could always do force of gravity that's perpendicular to R, that's still fine, minus force of 3 times lever arm of 3 equals 0. So force of 2, that's 9 newtons. What's that lever arm here? So on this one, that is from here to there, so that's 0.2 meters, minus the force of gravity. Right? The force of gravity is 1 newtons, and the distance from the axis of rotation here to that force? Well, there's 0.2 and 0.2, so that's 0.4 meters. And then minus the force of gravity, not force of gravity, force of 3 that we're solving for, and its distance, that's 0.2 and 0.5, so that's 0.7 meters equals 0. So let's see, that's 1.8 newtons times meters minus 0.4 newtons times meters equals F3 times 0.7 meters. So we got 1.4 newtons times meters equals F3 times 0.7 meters, and I get F3 equals 2 newtons. So even though I know it does not rotate like that, and that is really not the true axis of rotation, you can put the axis of rotation anywhere and still make the problem work. Again, we'll show you how that's going to be helpful in here in just a second. All right, here's one where there's missing values so you can see. So this is a good one where they'll let us see some stuff. So again, when we want to solve any problem, you want to be a kitten, so just relax. It's going to be okay. Then our free body diagram. So what forces, excuse me, are acting on the rod? Well, I have force of gravity, okay, of the rod. Then I have the force normal of the, what is that? Fulcrum pushing up. Okay. I have a normal force. These are kind of weird that it's really a normal force of this girl pushing down on the rod, but if I was looking at the girl as a box, I would say that her force of gravity is down and the force normal. Okay, and this is the force normal of girl on, force normal of rod on girl. And so we know Newton's third law that these are equal and opposite. So this is force normal of girl on rod. And so that these two are equal, so all three of these have to be equal. So really it's a force normal, but it's equal to mg of the girl. And so that's the same for the boy, mg pushing down. Again, it's really a force normal of the boy pushing down, but that's what we have. So where will the girl have to be for the system to be in equilibrium? So here I could do F net equals 0 or torque net equals 0. And the reality here is I need a location. Forces don't have locations, they're just forces, so let's not even waste our time here. That's not helpful. So now I have to do torque net. So I have to decide where I'm going to put my axis of rotation. So the actual axis of rotation is right here, but do we actually put it there to solve the problem? Let's think about what we have. Right? If I put the force here, right? Excuse me. Not the force, the axis of rotation. Then I have torque due to gravity of the rod. That would make it go in this direction. We'll call that positive. The fulcrum, torque due to the fulcrum would go up the opposite way or make it go counterclockwise. And then I would have plus torque due to the girl because she would make it go the same direction. So I know, do I know how heavy the rod is? Dang it, I don't know how heavy the rod is, so I don't know that force, so that's not helpful. Do I know the force of the fulcrum? I don't know that force, so I can't do it. So I have too many unknowns if I do that. So if we notice, you don't really want to put, you want to put your axis of rotation at unknowns if you're unsure of something. So if I don't know these two forces, let's put the axis of rotation right there. So that way, do either of those do a torque? The answer is no, because they are at the axis of rotation, so there's no lever arm. So then, the boy does a torque that way, and the girl does a torque that way. So I could say torque due to the boy minus torque due to the girl has to equal 0. I know their forces. And I know the boy's distance, so I should be good here. So I could say force of the boy times the lever arm of the boy must equal, because again, I just added this the other side, force of the girl, lever arm of the girl. Then you would just plug in your values and solve, right? Let's think if you could guess where this would be before we actually solve it. So if the boy is 2.5 meters away and he is 30 kilograms, where is the girl going to have to be? Is her number here going to be bigger or smaller? Okay? And so let's think about it. These torques have to be equal. Okay? So which one are we pulling down harder on? We're pulling down harder on the boy, so he has more torque if they were at the same location. If she was at 2.5, so he would win. So I can't pull down any harder with the girl, so what can I do to get more torque? And the answer is I can get farther away. So the answer has to be greater than 2.5. So test that one out and see what you get, and hopefully you get greater than 2.5. Alright, I'll end this video by getting you guys started on this problem, and then I'll let you guys, I'll put the keys, but you have to have your solid work is what you're going to turn in for your assignment right here. So let's take a look here. I need to find the mass, force, or distance needed to balance this going on. It tells me the mass of the rod is 4 kilograms. So we got to be a kitten, relax. Now let's draw our free body diagram. So the rod acts at the center. So these are all 10 centimeters, we'll say. So right here, I have force of gravity of the center of mass acting downward. Then also, what's touching the rod, I have a force normal of the rod pushing up. Again, we called these all normal forces. This is the normal force of 2, so I'm just going to call that the force of 2 pushes down. The force of 6 pushes down here. And the force of the question mark pushes down right there. Let's see, could I do just a net force? Because that's easier if I could possibly do that. So let's see, I have Fn going up minus F2 minus F6 minus Fg minus F question mark equals 0. So let's see, what do I know? Do I know the normal force? Nope. So that's an unknown. Do I know the force of 2? And the answer is yes. I know the mass, and so it'd be just mg. This force is just going to be mg. I know this force is going to be mg, so I know this force, I know this force. Force of gravity I know, because it's just mg there. But, I have this force right here. I don't know. So I have 2 unknowns, so I can't solve it. Let's try to solve it with torque, so we don't have to do a system. So again, torque net equals 0. So this is now where we have to decide where to put our axis of rotation. I will tell you, you want to put your axis of rotation at a location to get rid of an unknown. So I'll either put it at the normal force, or I'll put it at F question mark. Now, what am I solving for? I'm solving for F question mark. So if I put the axis of rotation there, that then doesn't have a lever arm, so it won't create any torque, so it won't be in my equation. I can't solve for it. So it's a poor choice. If I put my axis of rotation here, then this does no torque, so it's gone in my torque equation. And then cool enough, there's another force right there, so I don't have to worry about either of those if I make my axis of rotation there. So you'll see more later on, but it's really, really important to decide where you put your axis of rotation. So I'm going to put my axis of rotation here. So now I notice there's a lever arm here, there's a lever arm here, and there's a lever arm. So I have 3 forces creating a torque. Now, let's think about it. Which way, if I put my finger right here at this location and then came over here, this would cause a torque that's going that direction, so that's clockwise, so we'll call that negative. This one, if I held my finger here and pulled this way, it would cause a torque that way, and this one would also go. So we're saying both of these are positive and this is negative, so I would say the torque due to 2 plus the torque due to 6 minus the torque due to question mark has to equal 0. So then plugging this in, I would say that the torque is the force of 2 times the lever arm of 2 plus the force of 6 times the lever arm of 6 has to equal the force of question mark times its lever arm. The force of 2, we said, is mg times its lever arm plus force of 6. The force of 6 is m6. M6 times g times its lever arm and equals the last one. Well, that force is going to be mg times its lever arm. This is cool. If you notice, if you keep equations before numbers, you'll notice stuff will start to cancel out. There's a g in every single term, so it will cancel. So then let's put these masses in. Mass of 2, so there's 2 kilograms, times its lever arm. Let's see, how far away is it? That is 1, 2, 3, 4, 5. Let's see if it matters if we do centimeters. That's 5 centimeters plus mass of 6. That's 6 kilograms times its lever arm. That's 1 centimeter away equals the last one. This one is 1, 2, 3, 4 centimeters away. We don't know that mass times 4 centimeters. Again, if you notice, there's a centimeters in every single term, so they cancel. So my unit has to be left in kilogram. And be careful doing that, but this is a great one to practice your algebra. And again, your work, you'll be graded on that you have work to show that you have the right units. So here I have 10 kilograms plus 6 kilograms equals 4m. So I have 16 on this side divided by 4 divided by 4. So 16 kilograms divided by 4, so m equals 4 kilograms. So that box has to be 4. Okay. So that's how you set these up. I'll put the key, but your work will have to be detailed. So make sure you're going through all the steps. Detail it out. Make sure to spread that out so you can see that. Right. I'll start you on this one. Okay. So this is one. You can make the axis of rotation here at the center. Let's do our forces. So I have force of gravity of the pulley. The pin has to be pushing up, force normal of the pin, however that's held in place. Then I have the rope pulling down, and here I have the force of gravity, force of tension. This is where we start to get a lot of different things rotating. Right? So I have all of these. So we only want to look at the things rotating it. So that would be just these. Only those forces are causing rotations. So again, I'm looking for that F. So on this one, you could say my torque net has to equal 0. Well, I would want to make my axis of rotation the center because I don't know anything about the pulley or this normal force. So then I have the torque due to F because it would cause it to rotate this way. And then the torque due to tension going the other way. So I have force times its lever arm, which is right there, which is the radius of the inner, must equal the force of tension times the radius of the outer, is how that torque statement would be. So we don't know F. We know, I believe, this relationship, so you know both. You know radius inner, radius outer based off of those equations there, but you don't know tension. So this is now where you have to do a multi-setup of we know that this is not moving, so you should be able to know how those two forces compare. Okay? And I'll tell you those should be equal. So again, see what you can do. I'll be live on Tuesdays and Thursdays on Canvas if you need to ask me questions. Good luck. Miss you guys.